He's going to start the YouTube, but and we are live now. So,
okay. Oh yeah, there it is. All right, so I will take this as let me see if we're fashionably late enough. I think we should be slightly fashionably later, maybe another minute or so. So we have 31 participants right now. Let's see if we get any more in the next minute.
Yeah, I'm sure we'll get a couple more, but we're probably getting close. Yeah. Hi, Immanuel. Hi, Terry. Thanks for coming.
Okay.
Good to see you. Is Terry still here? He was here a second ago. Oh, yeah, there he is.
Yeah, I'm here.
I like your background. You're living in a library or something.
Sorry, I was muted. I'm saying I'm at home, essentially, which is very comfortable.
Maybe we should start.
Okay, I'm happy to start. So, all right, so I'm super happy to introduce Immanuel Bloch as today's first lecturer. And I'm really happy to see as well that the title of the slide corresponds to what was written down in the program. So that's always nice. So we'll hear about many-body localization, dynamics, and non-equilibrium systems. So Immanuel has been a central figure in cold atom physics. It hurts me to say this, Immanuel, but for over 20 years. I first became aware of him actually when I was doing my postdoc at NIST. I had switched from condensed matter physics, so I was before that blissfully unaware, and I switched into cold atoms and immediately was presented by these wonderful superfluid insulator papers. But my first real, I would say, non-historical research exposure was a really nice work looking at the presence of noise correlations and images of ultracold bosons and then later on fermions. And I thought that was amazing work, and I think it really embodies the type of work that you'll see that Immanuel's group does. And specifically, there have been a number of important technical innovations, including doing optical lattices, imaging atoms using single-site resolution that have been developed in this laboratory. And what's wonderful is that these technical approaches have then led to a wonderful, diverse range of physics. And I hope that you all students really get some neat physics and maybe some knowledge about how things are done as well from the lectures that Immanuel will give. So with that, I'd like to let you loose, Immanuel.
All right, thanks a lot, Ian, and thanks a lot for the invitation to give the lecture here. So I've planned 3 lectures, and as the title says, we'll try to cover broad set of topics covering many-body localization and some aspects of nonequilibrium dynamics in quantum many-body systems. And I think I had great lecturers before me. I saw you had David Hughes, Ehud Altman lecturing, and Vasim. So I got their notes and I know a little bit of what they talked about, and we'll build on that. But of course, feel free. I mean, this is school, right? This is not a colloquium, or we don't have to rush through anything. So you really have to slow me down, ask questions. I guess it's highly encouraged to ask questions during the talk also. It'll be a mix of slides and me deriving some equations and things and thoughts and concepts. So, and the best way usually is just to ask questions. And for me, this is also much more fun than if you ask during the lecture. So please feel encouraged to just jump in if you have a question, just shout. I guess that's okay with the organizers, or I don't know if you prefer another style. And
yeah, so I will also be monitoring the chat. So if you don't, someone has a chat question that you don't see, I'll jump in and let you know.
Very good, great. Yeah, so that's the precursor what I wanted to say before we start with the lectures. I hope you can see my screen. It's kind of a mixed iPad keynote experience with some good notes mixed in between. So 3 lectures. Here's the outline of what I want to cover, building somewhat on what you've learned before, but some concepts are also repeat. So I think it doesn't harm in a school to repeat some essential concepts again and go through them with you. So today we'll mostly focus on many-body localization, what we know from an experimental perspective about many-body localization in these interacting disordered systems in 1D and 2D, what we know what happens when we couple them to a bath, what we know about the entanglement dynamics. I think you've heard a lot about that. That's characteristic, and what we know maybe about potential instabilities that could prevent actually MBL from being a robust phase. So we'll try to cover these things today. Again, we don't have to cover everything in the lecture, so there's really no rush to get through everything. It's really much more important that you really get the essential concepts of what we're talking about, and you slow me down. So, and actually, I will also ask you some questions. So don't feel it's not only that you can ask me questions. I will also ask you some questions to also see whether where your level of understanding is, or whether we are missing some important points. And that's good feedback for me. So don't be scared if I ask you something. Okay. All right. Good. Yeah, lecture 2 tomorrow, we'll talk about actually extending these thoughts. We'll talk about thermalization in quantum many-body systems. That's, of course, very connected, because you might remember that these MBL systems are non-thermalizing systems. So we actually want to know how to probe thermalizing systems if today we talk about non-thermalizing systems. I thought it was also nice to review some older experiments from us on negative temperatures, actually what that means. I think it's an interesting concept for a lecture. And then we'll talk about non-equilibrium dynamics, Lieb-Robinson bounds, how fast information can spread in the many-body systems, how in these Hubbard systems we actually get to probe spin dynamics. And in the last lecture, I want to talk about a few of these dynamics experiments. And actually in the last part, I hope I get to that, something really new we have been working on for some time. And I think it's a very exciting topic covering mathematics, spin, and really very active field of research on Kada-Parisi-Zhang universality class. And we'll learn about what that's about and what we know about it and what we don't know about it, and where there are open conjectures and where there really, research needs to be done to solve those questions. All right. So with that said, let's get started with the lecture today on MBL and many-body localization. And you've heard about that phenomena before in David's lectures and in Ehud's lecture. And I took this slide also from Ehud, and this kind of epitomizes, I think, in pictures what we think about a thermalizing system is and what a MBL system is. So in thermalizing systems, you can start with some initial state. Let me actually draw here, and it could be your cup of coffee where you have milk and coffee separated from each other initially, and then over time, of course, this thing will mix, it will thermalize, and you will basically lose any trace of the initial state of the system. So the system here, you will not be able to say, did this system come from this one or something else? So you're basically losing correlations. In a quantum case, quantum correlations. And that's the typical behavior we have in most many-body systems, and we'll cover that actually tomorrow, how we can see that in a quantum system. Now, in the MBL systems, we find there's actually a different situation which is robust to imperfections in the system, where we can start in a similar kind of non-equilibrium situation where you actually have some information stored here, and we will find actually that in contrast to the thermalizing system, this will still retain information about this initial state for an infinite amount of time. Let me get rid of that, sorry. And for an infinite amount of time. And in our case, it will be quantum information, of course, that is retained for this system. Yeah? All right, so it's interesting because it's a case where statistical physics fails. Our usual approach is to statistical phases, and we really have to derive a lot of the concepts anew. So here's the general setting we're considering. So we're first of all talking about an isolated quantum system. Imagine this is the box, this is our experiment. It's isolated from the rest of the world, and we prepare some state in that system. And if we look at this could be even an eigenstate. Let's imagine we could prepare an eigenstate of the many-body system, which is of course really hard to do and usually impossible to do in experiment, but could be an eigenstate. And then let's look at a subsystem of that larger system. Okay, so we look at a subsystem A. When I mean look at a subsystem, I mean we measure some observables which only have support in this region A. That we not measuring a non-local observable which probes the system. For example, if this would be space, that doesn't probe the system at many points in space through the entire system, but maybe only probes it at local points within this region A, if that would be space. Now, what you find in this reduced state space here, if you derive the reduced density matrix of this system out of the larger system, you actually find for the thermalizing systems that it actually corresponds to a thermal density matrix. And I've written this thermal density matrix down here. So this is the classical form for your thermal density matrix. And interestingly, that's typically what you find for thermalizing systems. Right? Take a big system, you look at a subsystem, you find it looks thermal. Looks in like a thermal density matrix if you look at the density matrix of the system. And likewise, the so-called entanglement entropy or the von Neumann entropy, that is, if we write down the reduced density matrix of the system, subsystem A, log rho A, and take the trace of that, this entanglement entropy scales like the volume of the system. So we have what we call a volume law scaling of the entropy, volume law scaling of entanglement entropy, of this entanglement entropy. Okay, so that's very characteristic for thermal systems. And now we can, of course, ask when are there scenarios when this fails? And there are basically two scenarios where we know quite commonly where this fails. One is for integrable systems, where this fails. And in integrable systems, you basically have an extensive amount or an infinite amount of conserved quantities. And these conserved quantities constrain the dynamics of the many-body system so much that it cannot approach thermal equilibrium, for example, if we look at a dynamics experiment. And the second class that we're going to look at today are these MBL systems and what we can say about them in experiments. Now, the integrable systems typically are fine-tuned. So these are fine-tuned systems. So really you have to control your Hamiltonian parameters to a very precise degree to tune them precisely to that special point where the system is integrable. And only then will you have this non-thermalizing dynamics. Whereas the MBL scenario is much more general, and it's much more general and robust because it, as we'll see, it contains what we call an emergent integrability of the system. All right. So I think so far, I'm just repeating what you should have heard before, also in David's lecture. The prototypical system that people study in this context are spin systems, disordered spin systems. So you have a spins interacting here between site I and J. There's this spin coupling here that you see between these spins I and J, and that's typically random here. And then you can have also local fields, which could also be random. So you have local fields and you have couplings, and either one of them or both of them are random variables, okay, are distributed from a random distribution. Now, that's the physical system you start with. So this is the physical Hamiltonian. That's the real system we can Hamiltonian, we write down. And I think what David should have shown you, has shown you, or Ehud, is out of this physical Hamiltonian, you can actually derive an effective Hamiltonian, which is the one I've written down here. So this is an effective Hamiltonian that describes equally well the dynamics of the system. And this effective Hamiltonian now doesn't contain the original spins that we had in the system, the physical spins, the so-called physical qubits, but it contains the so-called logical qubits, the L bits, which again we can think of as, for example, spins in our case with tau x, tau y, tau z operators, similar to Sx, Sy, Sc operators in the system. And it turns out we can write the effective Hamiltonian in this following form as just as a product of these tau z operators, two interactions between two spins, between site I and J, effective spins, and like multi-point interactions, multi-body interactions, which become weaker and weaker as we go in the system. Okay, so we have an effective Hamiltonian that describes the evolution of our L bits. Now, what are these L bits? If we think of them again in terms of physical qubits, well, they're basically just some linear combination, some unitary transformation out of our physical qubits. So you take the physical qubits, you make a superposition state out of the original qubits, and out of that you get one bigger, let's say, tau qubit, which we denote by this state here, which this double arrow, which could be this up and down state or any superposition state. And it's made out of a superposition of these physical qubits. And what's also important to remind yourself that these L bits basically have exponential support on the physical qubits in the localized phase. So basically, if you think of, how many L bits make up one of these effective, physical qubits make up one of those L-bits, turns out this weight of these physical qubits that enter decays exponentially with distance. So that's where we say it has exponential support on the physical qubits, these L-bits. So now you can see that the problem is basically the problem of solving the dynamics of this interacting system can be converted in studying the dynamics of this effective Hamiltonian. Now, I should also say in any experiments, we never prepare an eigenstate of this effective Hamiltonian. Let's say an eigenstate of this effective Hamiltonian could be a state, so let me go back here, where we, for example, have these tau operators, these tau z's, and these tau z's point in specific directions. So this would be the tau z's on site 1, 2, 3, 4, 5, 6, and so forth, these L bits. And that would be an eigenstate of this effective Hamiltonian, as you can see. Now, we never actually prepare this. And since this would be an eigenstate, there would be no dynamical evolution also to this. So we never prepare this. What we typically prepare in the experiment would be a product state out of the physical qubits. If we can prepare something like that, for example, that would be maybe easy to prepare for us in the lab. And that state, you always have to remember what we can prepare in the lab is going to be a superposition state of the eigenstates that I wrote down below of the L-bits. So this state is actually going to be some superposition of those different L-bit eigenstates. Okay, that's also important to remember when we look at the dynamics of the system. Okay. So I hope that just reminds you what you've been taught before. We're going to use that actually in the following and some simple examples. We're sometimes just going to explain what's going on in the system by just looking at 2 of those L-bits and trying to understand what happens when we have 2 of those L-bits. For example, when we want to derive the entanglement properties of the system. And of course, everything generalizes to the more complex setup, but we can just derive this also in this very simple setting. Okay. Any questions so far? Any comments? Everybody good? Okay. All right. So just to say before we start getting going on some specific experiments and how we can probe this, I should say here are a couple of good reviews you can follow up on this. And by now, I think there have been really a huge host of systems where this MBL has been tested, cold atoms. I'm going to talk about those systems mostly today, ions and V-centers, electronic systems like superconducting qubits, for example, on the Google Sycamore processor. This has also been looked at, and we're going to look at an experiment from the Google team where they looked at specific properties. So you see that's actually very general in these artificial quantum many-body systems that we have today available. People are looking at this with a lot of interest. Okay, one other thing I want to stress, and maybe this connects, I don't know, Thierry, are you going to talk about disordered systems actually in your lecture, or?
Yeah, tomorrow I'll do the disorder a little bit, yes.
Okay, so probably in contrast to what Thierry is going to talk to you tomorrow, Thierry is probably going to talk about ground state disordered systems. What I talk about here, the MBL, is really a high energy density phenomena. So it's not in the ground state. That's also something you really have to keep in mind. It's not something that happens in the ground state of the system, but we're really probing the system at high energy densities. So that's really crucial. So here's just some numerical examples from studying these disordered spin models that you can see here. The toy model here of the MBL that we looked at before. We have this disordered spin system, and here's some just numerics of the system as a function of energy density. So here we have energy density. So if we go to the middle of the spectrum where we have, if we have a bounded spectrum, 0 would be ground state energy, 1 would be the maximal energy in the system. So we're also probing similar things to ground state physics, but we're really talking about something that happens here when you go to these energy densities right in the center of the spectrum. Okay, so that's the system that we're looking at. And here, even without saying what the quantities are that people use numerically to differentiate whether they're in the ergodic, a thermalizing phase, or in this many-body localized phase, I just want to different quantities here, and they all basically agree within their numerical approaches that they show. You see, this is really the regime we're going to talk about today. So how we can probe this high energy density region between this thermalizing ergodic phase and this MBL phase. All right. Leo, any question? Or I can't hear you, Leo. You're impossible to understand. I think you have to type your question in the chat. Okay, so here are a couple of questions that are interesting. I'll come back to those. Here are some important points I want to state right before we go to the experiment, because it's really important to what can we say in the experiment, what can we not say, you know, where do we have limitations. So first of all, what's interesting is that we want to understand MBL beyond 1D. So it's interesting from an experimental point of view to go to higher dimensions. Actually, David showed you even in 1D, it's not so clear whether this is a stable phase or has instabilities to it. So even in 1D, you see there's still discussions going on in the community. What we also want to show, and I want to show you that we want to make experiments, carry out experiments, which are very precise also in their characterization of the underlying parameters. And one caveat, one thing I always have to say, since we're talking about dynamical experiments, we're talking about transitions that we can observe in dynamical observables. So we're talking about long time evolutions that we need to see. And that always means we're going to be limited in the experiment. Because why am I going to be limited? Because remember, we have our system here. And I assumed the system is isolated from the environment. But typically, it's not really isolated from the environment. There's always some rate where we couple some large bath to that system, which will kind of render the system not perfectly isolated. And that also means that this small coupling of a bath to our isolated system will make it problematic for us in the experiment to say some things beyond some evolution times. So we want to keep this gamma, this coupling of the bath to our system as small as possible. So we want to push this environmental coupling as low as possible so we can go to as long as possible evolution times. And what I'll show you today in the talk, that we can go to evolution times up to 1,000, in our case, tunneling times or hopping times or spin exchange times. So that's where we're going to be able to say something up to those times.
Emmanuel?
Now, yes.
So Leo put his questions in the chat, and can I stop
Yes.
you before you go too far? So
Absolutely. Yes.
on the last slide, he was asking if the phase diagram was for Heisenberg or for the transverse field Ising model.
I think that was for this Heisenberg, this disordered Heisenberg. If I typed correctly, if I looked at Luis's paper correctly, this should be exactly the model I showed there, disordered Heisenberg.
Yeah, Heisenberg, but I guess all the disorders along one axis. It's not that you have a randomly varying disorder direction or something.
I think what has disorders in the Z field, yeah, just disorder as I wrote down here. So I think it has disorder in the Z couplings and disorder in the J couplings.
And then he also had a comment that, so you had this remark that it was interesting and little was known about the stability and dimension greater than 1 of MBL. And Leo's saying, well, David put some pretty convincing arguments that
I will come to David's.
It's not there. Yeah.
Yes.
So.
Well, I will. Well, again, so I think we have to make two things clear. First of all, any experiment is limited in observation time. This is not a caveat, a problem of our experiment. It's a problem of all experiments will be limited in their observation times. What I'm trying to show you today, we can go to up to 1,000 tau. And what I will claim, all my claims can be taken as claims up to how the system looks up to that evolution time, okay? If you're telling me, oh, my theory predicts that in 1 million tau or 10 to the 12 tau, it will be different, then the only thing I can say, well, maybe that's true. I will not be able to check it. Okay, I can't say anything about that. And that's very important to keep in mind always. But of course, from an experimental point of view, it's a challenge because we want to isolate the systems as good as we can. We want to make the coherent couplings in the system as good as we can. We really want to push to as long as possible evolution times. That's the challenge for experimentalists. Okay.
Great. And so I think that also that's a point that, you know, David did emphasize that there were important timescales where things would look different here. So yes. Just real quick, I do have one question before you go on. So the gamma here, are you going to tell us what is setting your gamma? What effects are
Well, right now it's just some general coupling strength to the system. We will talk a little bit more about maybe how that affects it in the discussion. We can talk about that, you know.
But I mean, why it's 1,000?
Okay, what does that gamma do? We can already intuitively say. So gamma will be a rate, how the bath couples to the system. And so 1 over gamma will give me a time scale where that coupling will become significant. Okay. So I can already tell you intuitively, I can already make an intuitive guess that up to time scales of 1 over gamma, yeah, the system can look like isolated systems. But if I go to much longer time scales than 1 over gamma, the system will sense that there is an environment and it will react differently. Okay. And this, I think, also comes back to what David, so I of course knew what David told you. I also read his recent paper. And here's the phase diagram that David put forth to you, you know, how this 1D system or the higher dimension system would look like. And this is what also, okay, this is not a proof what I think he had, as Leo said, had some convincing arguments. So I think this not settled this debate. But his scenario, his favored scenario was that as we, for example, crank up interactions or disorder here, we start from we can have a thermalizing phase in this region, for example. The system is thermal. And then there's a crossover into what he calls pre-thermal MBL phase. Okay, so that would be a phase which looks to me on the time scales accessible to me like a perfect MBL system. So all quantities that people have derived that tell you whether it's MBL or not. In this time here, let's mark this blue here. This would look to me as an experimentalist as a perfect MBL phase. Yeah. Only when I go to extremely long times, maybe 10 to the 12 tunneling times, I would, as I said, I would see, oh, the system is not really MBL, it relaxes also to a thermal state. But up to extremely long, can be astronomically long time scales, this system looks like a pre-thermal MBL. And then he says, well, maybe then in 1D, what they conjecture, there is a true MBL phase beyond a, let's say, even stronger, let's say, disorder strength, for example, in the system where the system really does not relax even to infinite times. Okay. All right. So I'm an experimentalist. All I can do is probe the system up to some time and look at its behavior. So I will not be able to answer this question. Okay. This is very clear. If this question is whether, you know, this happens at 10 to the 20 tunneling times, you know, or longer than the age of the universe, I cannot, this is an academically interesting question, but I cannot be able to answer it. So the only thing we can look at in this lecture is if there is this, what he calls a crossover, maybe from a thermal phase to this pre-thermal MBL phase, which looks like an MBL phase to me as an experimentalist over the finite time scales I have accessible. Okay, so that's also very important. It's good that we raise this point. Okay. But I would say that's a very general thing that any experiment has to deal with, right? It's not, again, it's something we will have to deal with. And the question then, of course, is, does something significant happen even more in the structure of the eigenstates that from here to here? That's, of course, an interesting academic question. All right. So let's start. Theo, yes.
I don't know if I'm breaking up or can you hear me?
Yeah, you're really very hard to understand.
Okay, sorry, I won't ask. Okay.
Just you're barely able to. Okay, so let's start and let's look at localization.
I had a question on the previous slide, if that's okay.
Yeah, sure. Go ahead.
What is the main factor limiting this time? Is it vacuum? Is it black body radiation? What kind of factors? What would you have to do to extend the time?
Yeah, vacuum can also be a limitation. If you start losing particles out of the system, that's, of course, particle loss would be bad. In our case, it could also be just technical noise. You know, we're trapping the atoms in optical potentials in lattices, as you heard, and these lasers shake or have frequency fluctuations. So the lattices will move slightly, they will shake, and all of these things are like heating introduced into the system. It's coupling from the outside, the laser noise, to the system. Okay, so the bath basically it would be, let's say, the technical fluctuations of your laser that couples to your system. Okay.
Okay.
Just to give you two examples. You're absolutely right. So these are very relevant for us to have technical noise under control, to push it to as low as we can. And for the best we can do today, and I think we really have the record times, evolution times, we as I said, we can go up to 1,000 tau. That sets you to 1,000 tau.
Is that 1,000 tau for both 1D and 2D?
Yeah, that's pretty much the same. Yes. Yes.
Do you think that an increase is possible, or it doesn't make sense, or are we kind of at the limit of technology at the moment, and like there's no way we can extend this by 10 or 100 in the near future?
Oh no, I hope, of course, I hope we can extend this by a factor of 10 or 100 in the future. We can also go to larger systems. Yes, of course, I hope that. Beyond 100, I'm not so sure, but 10 to 100, I'm hopeful. I would be hopeful.
Okay. Okay.
So maybe
Thanks.
then going to 10 to the 5. But the question is, does that qualitatively change the question that David has been answering? You know, will it
Right,
be
you're talking about 10 to the 12. That's what I'm asking. It doesn't
Yeah.
make sense even trying to get to 10 to the 12, right? That's kind of where I'm coming from.
This is really as astronomic timescales, and I will never be able to check it in any experiment. Okay,
Right, that
but it
doesn't-
still might be an academic interesting question. All right, good. Okay, so let's turn to localization. And the first phenomena I want to show you, I just want to give you the spirit of how do we check for localization. Well, for localization, we can just, start with a particle. For example, if we look for non-interacting localization, Anderson localization, we can put a particle in a system. We can monitor how it evolves over time, how it spreads in space, for example. And if we put it into a disordered, for example, potential, we know that we have the phenomena of Anderson localization for the non-interacting particle. And this has been beautifully demonstrated in optics experiments, in cold atom experiments. People have seen this wave function. Here's a density of the density distribution of the atoms as they spread out in this disorder potential. And you can really beautifully see this exponential distribution of the probability distribution, indicating this exponential localization of your particle. The spirit of what we're going to do with MBL is actually very similar, and we'll talk about this in a second. We're going to prepare a non-equilibrium state, and we're going to look at the dynamical evolution of that non-equilibrium state. So in spirit, we're going to use a very similar probe. Okay. All right. So the first system I want to study with you is this disordered Fermi-Hubbard model. So we connect to Wasim's talk, and also I think what you've heard from the others and theorists. We have fermions hopping on a lattice. So we have C-dagger C operators, which describe this hopping in one dimension. Then we have an interaction between the particles U here. When two spin up and down particle meet on the same site, they interact. We can tune this U with the Feshbach resonance. So this allows us to tune the interaction strength from non-interacting to repulsive interactions to attractive interactions. And then we have the disorder potential, although it's not really disorder, it's this incommensurate modulation of the on-site energies. So we have an incommensurate lattice potential with the original lattice potential there. And this parameter alpha characterizes how incommensurate this potential is. And we choose this alpha, in our case, 0.721. That's just convenience of the laser fields that we have. So it's not supposed to be, for example, 2 or 4, right? It's not supposed to be a super lattice. We're going to talk about those in a second too. It's really supposed to be a incommensurate number that doesn't allow the lattice to repeat itself over long time scales, long length scales in the system. Okay, so this is the incommensurate potential. It lifts the local energies up and down by this amount, maximum amount delta. So this is the strength of the disorder potential, the strength of the potential. And this is our basically parameter that denotes how incommensurate system is with the original lattice potential. Okay, this is the so-called Aubry-André model. And if we forget about U, we have this non-interacting Aubry-André model that has been studied a lot in the literature. So we basically know everything about this system. And that's good because we can use this system always as a reference system to go back to when we turn on interactions. So we can start with a non-interacting system where we know basically everything also from numerics, and then turn on U and see how the behavior is different in the interacting case. Okay. Okay, so what do we know? What do we know about the non-interacting system? The Aubry-André system is that for delta over J smaller than 2, all the eigenstates are extended. And for delta over J larger than 2, all the eigenstates are exponentially localized. So let me show you that. So here I just diagonalized the system, and I plotted the ground state wave function that you can see here. So let's say the wave function weight, this would be my lattice sites on the vertical axis. I have my lattice sites. Here's disorder strength. So if I'm below 2, here's this magic parameter 2. If I'm below 2, you can see how this wave function is extended across the system. And once you tune above 2, you can suddenly see how this wave function becomes localized. Okay. And if we plot this on a logarithmic scale, we could see that it's actually exponentially localized, becomes more and more localized as we crank up the disorder strength. We can actually write down, we can calculate analytically the length scale, the decay length of this exponentially localized wave function. And this is this localization length I've written down here. And you see it scales like 1 over the logarithm of disorder strength over 2j. So we have this logarithmic divergence as we go from high disorder strength to low disorder strength. So for high disorders larger than 2, for delta over j, this is here our delta over j larger than 2, we are here localized, and here we have these extended states. And in principle, for an infinite system, you would see that the localization length diverges in this system. Now, for a finite system, we're looking at finite systems, right? So what happens for finite systems? Well, for finite systems, you're always going to have a cutoff. For example, in our harmonic traps, we often don't have box potentials, even though now, I'll show you in the end of the talk, we can also make nice homogeneous box potentials. Typically, we always have a harmonic trap. Yeah, Thierry's happy now. Now we can do that. Yeah, I show you. We really do nice boxes now. But most experiments don't have these boxes. They have a harmonic trap on top of the lattice. And that will mean that this divergence will just stop at some point. It will be rounded off because of this trap effects. Okay, so it will really, this is some, effects that come in due to the trap, harmonic trap, and that will basically cut off this divergence, just to show you the full picture of what one typically sees in the experiment. Okay, good. So now in the spirit of, we know everything from the Aubry-André model, let's then go to the interacting system and let's just conjecture what we expect there, okay? So we want to prepare an initial state, which is not the ground state of the system. And for reasons I'll show you in a second, we choose these charge density waves. So this is what we call a charge density wave, where, for example, every second site is only populated our lattices. And this is something we can prepare actually very nicely. We can also read out very nicely, even without single site resolution of detection. So this was done a little bit before that age. It actually offers a very nice detection. I'll show you how we can do that. So now we can also prepare those states. And we look at the dynamical evolution of this state. So that's the initial state, and we probe it over time. So what do we know as a function of interaction strength in the system? So this is U over J. And we want to know what we know, what we can tell. Okay, so for U over J0, we're in this Aubry-André model. And there we know everything, right? In the Aubry-André model, we know for delta over J smaller than 2, we are extended. For delta over J larger than 2, we are Anderson localized. So here we know there's a transition from extended states to localized states in the non-interacting model. We also know in the infinitely interacting model, we know another reference point, and this is important. We know also for infinite interactions, if we do not have doublons initially in the state, in the system, so we only have occupation 0, 1, 1 on the lattice, so no doubly occupied sites. We also know that this infinitely interacting, infinitely strong repulsive interacting model maps onto the non-interacting problem again. So we know that mathematically. So it's exactly the same as the non-interacting model, which means we have the same behavior. Also here we know that for infinite interactions without any doublons in the initial state, we have extended states here and we have localized states here, okay? And now we can conjecture what happens now in between. Well, we can think that probably interactions will destabilize our localized phase, and we might need larger disorder to localize it again. So it's not unnatural to come up with something like the curve that you can see here that will have increased. We might need some larger interactions to localize the system again, but then we know this has to fall off to come to this point again over here, okay? So that's just totally conjectured, what I show here, but kind of a reasonable conjecture, and we'll try to see if that makes sense. Okay, how do I probe the system? Probe the system through measuring the so-called imbalance. This basically is the imbalance is kind of the visibility. So this imbalance is the visibility of the charge density wave. So the imbalance corresponds to the visibility of my charge density wave. So it's like a contrast of an optical interference pattern. Okay, it's like the maximum intensity minus minimum intensity divided by I max plus I min. So it's like a contrast of this charge density wave. Okay, so it's like a contrast of this charge density wave. And this is something we can monitor actually very well in the experiment. Okay, so let me briefly tell you a little bit about why we like this state, why we can prepare it very well, and how we can actually monitor its dynamics in the system. Okay, and for that, I just give a brief interlude on these optical superlattices. So this is not the Aubry-André incommensurate lattice, but a superlattice where we basically superimpose two optical lattices, one at one wavelength, for example, here 1530 nanometers, with another optical lattice, which is precisely half the wavelength. Okay, the combination of the two is what we call a superlattice. And now in the experiment, the nice thing is we can control the amplitude of the blue wave, the amplitude of the red wave completely independently, because we control their intensities independently. These are just two laser beams at two frequencies, which we control independently. And we can control the relative phase of those two standing wave potentials also. And all this can be done dynamically. So if you think about what is the potential I get when I sum up the red and the blue potential, it's something that you can see here. It's this array of double wells. And by controlling the amplitudes between the different laser beams, we can control the intra-well depth, the inter-well depth. We can control through the phase. We control whether this is tilted or not tilted. You know, so we can change here the inter-well barrier depth. We can also, through changing the phase of those two superlattices relative to each other, we can tilt the double wells relative to each other, and all this can be done dynamically. So this is, of course, nice because this is, for example, a way how we can prepare the charge density wave. So you can immediately see I can prepare the charge density wave in the following way, that I load my atoms, my ultracold atoms, into such a potential where this is biased, where this every second well is lower. So now all the atoms will go into these lower wells. And then when I jump back to the original system, if I rapidly change back to this configuration, I will still be in a configuration where the atoms are only on the even sides, for example, right? And then I can initiate dynamics by now lowering the potential. I can now lower the potential barrier depths to initiate some dynamics, some tunneling dynamics in the experiments. And this is how I can initialize the charge density wave in the system. Okay. This is also nice because you can do this in 2D also, these super lattices. You can create also some interesting, plaquette configurations if you have these super lattices in 2 dimensions available to you as well. So I briefly want to explain to you how we can actually probe now use this also to read out. So you know now how we can prepare the charge density wave. Let me now explain to you how we can read out the imbalance in the system as well. And for that, I want to make use of something that we call band mapping. It's a very nice technique how we can reveal the population of the different energy bands, the quasi-momenta in the different energy bands in the system. So what I plot here is for a simple one-dimensional sinusoidal lattice, I plot the band structure. So this is energy here on the vertical axis versus quasi-momentum or crystal momentum on the horizontal axis. And you should know how this looks. Remember from your condensed matter physics course, for free particles, you have the p squared over 2m parabola. If you fold that back into the first Briand zone, it looks like this. And then because of the lattice, come back again, you will get gaps opening up at these points here. And these are, of course, the band gaps that we get in our periodic system. And then you get a band structure like what you see here for increasing lattice depths to the left. So here we would increase the lattice depth, 4 recoil lattice depth, 20 recoil lattice depth. And you can see how this becomes more and more flatter. The separation between the bands increases and the bands become flatter and flatter. Do you know why the bands become flatter and flatter? Do you have an idea why they disperse less? Why does the separation approach this one value here?
They get a lot heavier, right?
They got a lot heavier. That's correct, because that's determined by the curvature of the band. But in this limit, let's say we would go to infinitely deep lattices. How could I think of this lattice, this periodic lattice? Somebody know?
Just get potential wells, right? Infinite wells where you have a flat
Infinite, right? Infinite, what kind of wells? Infinite.
Square ones, eventually.
Not square wells in this case, almost right.
Harmonic oscillators.
Right, in this case will be almost harmonic oscillators, right? If we go to very deep lattices here, they will look locally just like harmonic oscillators. And if this is very deep, these are just decoupled harmonic oscillators. And then we have the ground state of the harmonic oscillator, we have the first excited state of the harmonic oscillator, and so forth. And this energy separation then between the bands for very deep lattices, that's just the energy separation between the ground state and the first excited state of your harmonic oscillator on a given lattice site. Okay? Okay, that makes sense. All right, so let's imagine now you prepared a atom with a Bloch wave in the band here. Okay, let's say you are in this deep lattice and you prepared an eigenstate of the single particle system with such a quasi-momentum Q, and now you adiabatically lower the lattice depth. So what's going to happen? What would you say happens if you adiabatically lower the lattice depth to this particle in that specific state? Any ideas? So we just go from here, this deep lattice, to a shallower lattice. Eventually to a free particle case, but let's just for now just make the lattice shallower and shallower. So what happens?
When it adiabatically follows the crystal momentum?
Okay, so let's go to 4 recall. Where do I draw my point now? At what quasi-momentum?
In the blue line further down, like at the same K?
Exactly. So first of all, we're not applying any force. So we're not changing quasi-momentum to the system, right? And we just ramped down adiabatically slowly. So we're just staying in the same quasi-momentum and we're staying in the same band. We're not making transitions to other bands. We're staying here. And eventually this goes down. Now, if you ramp to the free particle case, when you ramp down the lattice completely, you're just back to the free particle case. And now you don't have a Bloch wave with quasi-momentum Q. Now you have a free particle with that quasi-momentum Q, H bar Q. And that's now flying out of your system. So actually this you can see maps onto a free particle with quasi-momentum Q, and that now extends to all other bands as well. And you can see if we would now have actually a particle in this excited band, the same thing would happen. Yeah, this would go here, but now we have to unfold our parabola to give us the free particle p squared over 2m parabola. So this would show up as a particle in the second Brion zone up here of the system with a free particle corresponding to the quasi-momentum of that system, but now in the second Brion zone of the system, whereas the particle in the ground state band was going to show up as a particle with the momentum in the lowest Brion zone of the system, okay? So band populations get mapped onto Brion zone populations, and these are now free particles that fly off with a specific momentum. Okay, and this is really works. So I can show you this here. So here's a picture that we took when we populated all the Bloch waves in the lowest energy bands equally with equal weight. And then we just did this adiabatic mapping. And now you can see that you get this perfect homogeneous distribution of the atoms in the lowest Brion zone of the system because each of those quasi-momentum states was equally populated. And if we do this with higher bands, you can see now how the higher Brion zones are populated. Again, this picture tells me, if I look at this picture, how was a Bloch wave here with this quasi-momentum, which is now free momentum, how was that populated in the second band of my system? Okay, because it's appearing in this second Brion zone. I know it's coming from the second band of my system. And the point where that is populated tells me what quasi-momentum that was. Okay, so from this adiabatic band mapping procedure, I can actually derive, I can know what the population of the different energy bands was. So let me just show you this, how this works then if we want to do this for our superlattice. So imagine we have our superlattice potential we have, and we want to measure the left-right imbalance. So imagine we have some particles here and some particles here, and they are in the ground state band, and I want to measure this even odd particle number. What I can do is the following. I can dynamically change my double well to the following configuration, where the green particle stays over here in the lowest well, and I lift up my potential here and move it above resonance of this state. So I move this continuously up. It moves through resonance with this state. And if here's a tunnel coupling, then you're just going to have some adiabatic transition where you're basically going to transfer the population from over here to over here. So what's going to happen after you did this sweep, you're going to end up with a population on the left well in the higher band of the system. Okay, now if you're in the higher band of the system, well, now it's the total system configuration would maybe then look like something like this. So you are in this configuration with every odd side here. This is the odd population. This is the even population. After you did this detection scheme, odd, even. And then you do the band mapping. Now you do the band mapping. And then what you're going to see in momentum space, you can basically see that these red particles will appear in the lowest Brion zone. Can just count that, the particles here in the lowest Brion zone and the particles in the first excited band, first Brion zone, second Brion zone, sorry, these here, these were from the, I drew it, sorry, the colors are just the opposite. So just reverse green and red. I hope nobody's red and green blind. So apologies for that. So I just reversed red and green here. So red should be outside here and green should be inside. And then by just counting the number of particles in these Brion zones, I can originally reconstruct what my even odd population was like. Okay, so that's why we like the super lattices, because we can nicely prepare these charge density waves, and we can also read them out very efficiently.
Immanuel, there's a question from Anant.
Yes.
Yeah, I had a question about the band mapping. So you said you have to adiabatically lower the lattice step.
Yes.
So in that case, towards the end of the ramp, I guess the band gap closes, right? So do you, towards that part, will you just go quickly over the?
You're completely right. There could be some non-adiabaticity at that point, but that's just going to affect very few particles, right? Because it will only affect the particles over here, right? In this region, where the band gap in the middle, there's always this energy gap here. So we're perfectly fine there. We're going to could be problematic to those particles out in those regions. It might change a little bit the population here. That's right. And depending now how slow you ramp, it will affect more or less a larger region or a smaller region in Q space, in momentum space. Okay.
Oh, okay. Thanks.
Okay, good. All right. So now we do the experiment. We prepare the charge density wave. We turn the disorder in the Aubry-André model to a certain value, and we turn the interactions to a certain value, which is the U over J parameter. And then we let the system evolve over some evolution time. And then we read out, after that evolution time, through the technique I just showed you, we read out the imbalance again in the system. So we probe the imbalance. So let's first look at the non-disordered system, delta over J0. So there you can actually see that even if we have interactions, the system very rapidly decays and there's zero imbalance. I mean, it just populates even and odd sides equally. I mean, you just have no disorder. It just smears out this initial density wave, very rapidly decays. But now if you go to delta over J3 or delta over J8, you can actually see that, well, even for long evolution times, well, now we come back to the point I made initially, up to, let's say here, 30 tau or 50 tau that we looked at in these first experiments, you can see that the imbalance has a non-zero value. And that is incompatible with a thermal state. Because for a thermal state, there would be no reason why even or odd sides should be not equally populated. Right? For thermal states, there should not be any unequal population of even and odd sides. So the fact that we see this imbalance persist up to 30 tau here directly tells you this is not a thermal state at 30 tau. Okay, so that's an important point. Okay, just to show you that interactions do play a very important role in the system, we did this also. Yeah.
One more question from Leo. It says, are oscillations associated with the tunneling time scale, 1 over J?
Yes, yes. These initial ones, the ones in the beginning especially, are just oscillations, yes. Yeah.
So Immanuel, can I ask a devil's advocate question here?
Sure, sure.
So if I did this experiment with reasonably well-occupied bosonic coherent states, I could see macroscopic self-trapping type of phenomena as well, which would, in this left-right imbalance situation, give a pretty similar signature. I would see oscillations, I would see long time imbalances.
Right.
So-
And you would also conclude, I guess, from that, that up to that time, it's not a thermal state, right?
Yeah, exactly. That set of conclusions would be common.
Yes, yes. So we have to do a few things more. We'll come to things more that we can probe, but let me just start with the simpler things and then go to more advanced things that we can look at to distinguish this dynamics from other dynamics you're pointing out, Ian. But you're completely correct. Yeah. That brings us to an important point, actually, to show that system is non-thermal. It's much simpler than to show that a system is thermal, because to show that the system is non-thermal, you only need to show in one observable that it assumes a non-thermal value. Then you can say already, well, that cannot be a thermal state. If in one observable, just one that you pick that is best suited for you, you can show that it's non-thermal expectation value, then you know that the underlying state cannot be a thermal state. And so we pick the imbalance in this case as a simple proxy. So now here's actually a nice experiment we did just to show you that interactions do play an important role. Here we did the same experiment in 2D. So we have a 2D quasi-periodic setting. Again, we know there's basically Anderson localization in the non-interacting model. And that's also what we see. So we go to the non-interacting case here. This is the green curve. This is U equals 0. In the 2D case, we start out with the initial populations. Then because the Anderson localized wave function is not really on-site wave function, it's a little bit more extended. This spreads out, decays a bit. So our imbalance will be reduced a little bit here and then converge to this value here. And we'll then assume a steady state value. Now, what's interesting is when you do the same experiment in 2D, and you just turn on interactions, you can clearly see that, for this U equals 5J case, you can immediately see that now, obviously, we're not in a not in a localized state anymore, but now we just see this decaying imbalance showing us that is a completely different dynamic. So interactions really make the system behave profoundly different for the absolutely same disorder and underlying lattice potentials. Okay. All right. Good. So let's go back to our reference point where we understand things well. Here's the imbalance as a function of disorder strength for the non-interacting system. If we would have no harmonic trap, then, as I said, we would expect for a delta equal 2 localization to occur. And starting with delta equal 2 localization to occur, we, of course, immediately should expect imbalance to increase. So immediately when we cross the transition to localized state, immediately the imbalance should rise because now you're favoring more localized wave functions. And then if you have an initial charge density wave, it won't be smeared out completely. And this is indeed what you see. You can see that actually if you have a real experiment where you have also harmonic trap underlying, this is smeared off a little bit. You don't have a sharp rise here, but a more gradual increase. But the exact diagonalization result agrees perfectly with what we see in the experiment. So the experiment is the data, and the red line is what theory predicts. Okay. So I think that just shows we understand the system, we know what it's doing. Okay. Now let's do the same experiment with the imbalance now with the interactions with this order. And now you can see the situation looks different. We basically at the U equals 0 point here, we are non-interacting. So here we have basically the Anderson localization point that we can see. And now we can see that if we increase interactions, we actually need a larger disorder to localize the system again. So if we would not increase the disorder, we stay at the same disorder and just increase interactions, we lower the imbalance until at very large interactions again, we increase this imbalance again and go back to a more localized state again, okay? So this conjectures then that there is also a transition from the extended states to localized states within this evolution time, which we hope is the steady state of our time evolution in the system, the true steady state of the time evolution in the system. And we then would conjecture from this picture that the transition would occur somewhere in the regime here, delta over J3, where the imbalance rises here encoded in this color from 0 to this finite value that you can see here, okay? All right, there's another thing that you can actually nicely see, and this is actually numerics now, and we'll derive this in a second. And we'll actually also see how this can be measured in the experiment. This is the growth of entanglement entropy. So this was a Hoots group at the time. They did the numerical calculation using matrix product states. they calculated the entanglement entropy for our system. They looked at it for different interaction strength. And you see basically for the non-interacting system, you just have a quick increase of the entanglement entropy until it reaches steady state here, Anderson localization. And then in the interacting case, you have this characteristic log T entanglement entropy growth. And if you compare that entanglement entropy growth, this slope of this log T function here, what you see here, to the imbalance, the steady state imbalance that you see under these conditions, you actually see that you can actually see that this is kind of like a mirror image. So the blue is the slope of the entanglement entropy as a function of the interaction strength in the system. And you can see that entanglement entropy slope rises here, increases. And at the same time, we reach a minimum in the imbalance, which we would expect to occur for like more delocalized states in the system. And then when the system becomes more localized again, we still have a log T growth, but with a much smaller kind of slope for the entanglement entropy. Okay, so I just want to quickly ask, how familiar are you with this log T derivation of this log T entanglement entropy growth? I mean, is this clear? I have prepared a few notes. We could derive it quickly together. Where this comes from, or did you cover this already with David and Ehud again, and I would be the third person to cover it, so might not want to do that again. So maybe you give me a hint on how we should proceed here. Should we quickly derive that together, or should we just accept it as known? Derive?
Yes, well, I suggest.
Okay, let's do it quickly together. Let's derive that. Okay, so let's do it just for, as I said, we're going to very often when we do the derivation, we're just going to use a simplified model. Remember, we have these LEOMs, these local integrals of motion, which were our tau z operators or tau I spins, and that we had set of tau I operators which characterize these L bits. And let's just consider the case where we have basically two of those LEOMs interacting with each other. So remember, they have these exponentially localized states made out of the original physical qubits. So we have these two LEOMs that we want to have interacting with each other. And so we have, let's denote the spin states of this LEOM as up and down here for this first LEOM, and spin state up and down for the second LEOM here. So this would be 1 and 2. And now let's consider the interaction Hamiltonian. Our MBL Hamiltonian for this system would be just the effective Hamiltonian HI tau IZ with I running from 1 to 2. And then we have the interaction between the two spins that we can have here. So we have basically just this J12 tau 1Z tau 2Z interaction. Okay, so that's, and then there could be higher order terms, but let's forget these higher order terms that are there. And now let's just remind ourselves that the strength of the coupling J12 in the system, this would be some proportional to some bare coupling strength J0 and would be exponentially decaying with the distance between those two LEOMs divided by some localization length that we want to think about. And now let's consider a general initial state that we can have. It would be a superposition state, as I said, of these different tau z states. So let's consider, for example, a state where I have the first LEOM in the state, for example, A1, LEOM up 1 plus B1 down of my first LEOM, and tensor A2 up 2 plus B2 down 2. And well, let's, for simplicity again, let's set all these coefficients to 1, just to have equal weights, and just for sake of argument to see the dynamics of the system. So we basically have an initial state 1/2 up plus down, tensor up plus down for the second LEOM. Okay, so that's our initial state. So that's psi of 0. And now we evolve it according to the effective Hamiltonian. the psi of t that we have here, okay? So now we evolve it according to the effective Hamiltonian, and then we can immediately see, well, the up and down spin configurations that we're going to get are going to have a different time evolution than the up-down spin. So we're going to have 1/2 minus I j12 times t times the up plus down configuration plus 1/2 e to the I j12 t times up down plus up down spin configurations. Okay, is that clear to everybody? So that's basically what I have in my time evolution of the system. And you can immediately see this becomes a non-product state. This becomes an entangled state when j/1 times t equals to pi/4. So this state is fully entangled. For j12, the coupling strength between the Lioms times tau t equals pi/4. Okay. Then I will get a non-separable state again. I will get a fully entangled state. So let's generalize this for a, let's say we want to know now how distant apart are the spins entangled at time t. So we know at time t, the condition for entanglement is that j12 times t is on the order of 1. This is our pi/4. Let's say this is just 1. And we know that j12, that's just g0 times e to the minus x12, the distance between the two Lioms, divided by xi times t is on the order of 1. Okay, so that means my that just means my j0 times t is proportional to e to the x12 over xi. And now I can just take the logarithm of this, which means that the distance over which my two particles will be entangled at a time t, x12, that's just proportional, going to be proportional to xi, this localization length of my Lioms, times log xi, log j0 times t. Okay, the coupling strength in my system. And this distance over which the spins are entangled, that's just proportional to the entanglement entropy of my particles at that distance. Yeah? So, so this basically shows you, and this would hold now for an arbitrary, length of spins. We just calculate up to what length are the spins or the Lioms entangled at times t, and we find, because of this exponential decay of the support in the physical qubits of our Lioms, we directly get this logarithmic entanglement entropy growth in the system. Okay, and this xi here, this is our localization length of the Lioms. And now we see, again, we can connect this to the experimental result or to the theory result in the numerics. When the slope of the entanglement entropy was large, this was meant there was a large, basically, localization length in the Lioms. And then, of course, the imbalance had to be small. Okay, so that nicely explains why this mirror image between the imbalance and the entanglement entropy growth is reflected in each other. Okay, I hope this wasn't was helpful. So this length, is it clear to everybody why this length gives me the entanglement entropy? If I do this for a spin chain with L particles, is this clear to everybody why the length over the distance will give me the entanglement entropy? Think of it like this: if you have a spin chain of length L or length X here, then how many states are in that? How many microscopic states can there be in that length L system? Somebody want to say? So how many states do you have? How many states do you have in a spin chain with L spins? How many configurations?
2 to the L, right?
Sorry?
2 to the power L?
2 to the power L, exactly. So you have the number of possible microstates is 2 to the number of possible states is 2 to the L. And if you take the logarithm of that to calculate the entropy of the system, you get something that's proportional to L, right? And this is why this L, this length here, directly is proportional to the entanglement entropy in the system. Okay, very nice, correct. Okay, so this tells us how we can derive this entanglement entropy growth, this celebrated log T entanglement entropy growth. And now going back to the data, we can actually, or to the numerics, we can actually now understand why this large slope in the entanglement entropy growth is connected to the small value of the imbalance you get. And remember, this W shape that you get here for the system, this is exactly what we saw in the experiment. Okay, this behavior of the imbalance as a function of U over J is precisely what we saw in the experiment. Okay, so there's another point we can check that I showed you. I told you that mathematically we know if there are no interaction, no doublons in the system initially, and for infinite interactions, we should exactly recover the non-interacting system again. Okay, if we prepare an initial state where there are initially no doublons, we let the system evolve over time and there are no doublons there, then we should get the same result as in the case of the non-interacting system. So here's the non-interacting system, U over J0. We evolve the imbalance over, let's say, 50 tau, and we see this is the steady state value we get. And then we do exactly the same evolution for something that has very strong repulsive interactions, U over J20 here. And we have no doublons initially. That's important. No doublons in the initial state. And you can see that the value we get for the imbalance is precisely the same value we get as for the non-interacting case. So that squares out as well. So that works. So what we actually mathematically know is a mathematically exact result, we can also see here in the numerical data. What we actually also see is interesting. If we do have doublons in the initial state, so if we do increase the doublon fraction in the initial state, then actually the imbalance increases, meaning that we need a lower disorder strength to localize the system. But that also makes intuitively sense, because if you think of these doublons as heavy objects that don't move, don't have a kinetic energy or T or J, as I write it down here, but actually can only hop in second order processes like J squared over U, then these doublons have much lower kinetic energy and you need much less disorder strength to localize them. So for a given disorder strength, you would think that the doublons are much more localized than the singlons. And basically this means that you would then have a larger imbalance in the system, which is also what we see in the experiment. Okay. All right, good. So 1D covered. Let's go to 2D and apply the same logic to 2D experiments. Okay. So we do a similar experiment, but here we're not going to work with the Aubry-André model, but we're going to work with real random disorder. We're going to work with the Bose-Hubbard model, and we can have interacting systems, and we're going to again look at the dynamical evolution of the system. But the spirit of the experiment is going to be very similar to what we learned in the 1D case. Let me first show you how we realize the disorder potential. So disorder potential on top of the optical lattice, we realize by projecting basically a fluctuating intensity pattern of very short length scale onto our optical lattice. We do this with these so-called digital mirror devices, where we have pixels that we can turn on and off. And here you can see some of these pixels that we turn on and off to create an intensity pattern like that. We send it through our objective, which has a finite resolution. So it convolutes the image, the DMD image, onto our atoms, and this is basically the disorder potential that the atoms will see. The higher resolution your objective is, the shorter range, the sharper this DMD image would look like. So there's just some smearing from imaging this DMD disorder pattern through the objective. Okay, so now the nice thing with the atoms is we can really go in and measure this disorder side by side, because it lifts the energy levels up and down, remember, on a given lattice side. We can spectroscopically map out the disorder potential by just looking at the response of the atoms in our system. And this was done here in this experiment where we measured side by side. We measured the offset, the energy offset at that lattice side. And this is what we expected from the calculation. And you can see actually it works out quite well. So you see this ring here that we expect is precisely this ring that we see here on the atoms. This blob here is this blob here. So it actually works quite nicely. What we project, what we do program onto our DMD device, really the atoms experience then. So we have a very, very well characterized and very well controlled lattice potential with this characterized disorder. That's nice because, you know, we can now even build in strange correlations into the disorder pattern if we want to.
Immanuel, Leo has a pretty extended question there in the chat that.
Okay, do you want to?
Yeah, so there's an assumption here that the entanglement grows to a volume law in this LT region, does the asymptotic entropy of T go to volume law? If
Yes.
so, this seems to contradict the fact that it is an NBL state that does not fully thermalize.
No, but
So
wait.
is S,
Yeah. So indeed, so the maximum entropy, so go back to this state here, this numerical calculation. So this curve will of course saturate, cannot go larger than volume law entanglement. So this curve will have to saturate at some point. And the statement about MBL is of course the statement on eigenstates. So whether we have area law entropy, entanglement entropy that holds for an eigenstate in the tau z basis. So if you pick an eigenstate of my Leoms, that state would have area law entanglement entropy. But remember, I told you we never prepare in the experiment eigenstates in the tau z basis. We can prepare an eigenstate in the Fock basis, which be a superposition state of the different tau z bases that we have. And that's why we can even see this dynamical growth of entanglement entropy. If you would prepare an eigenstate, an MBL eigenstate in the tau z basis, it wouldn't show any entanglement entropy growth at all. But if you would just calculate its entanglement entropy, it would just have area law entanglement entropy. Did that answer the question? No, nobody.
so Leo says ... Is the cutoff of the volume law L smaller than the thermodynamic one?
The coefficient, is the coefficient still smaller than thermodynamic one?
Yeah, that's a good question. I think this depends a little bit sometimes on the system, how large, where this, you're asking, what you want to know is where does this thing go to, you know, which value does this go to? Does this go to full volume? I think this depends, as I said, this depends very much on your initial state. Because I said, if you start with an initial state, which is in tau z eigenstate, there's no entanglement entropy growth at all. You just have area law entanglement entropy. If you have, let's say, a superposition of all the possible tau z states in your initial state, then this would probably go to volume law entanglement entropy, to the maximum possible entropy. But it really depends how your initial state decomposes to what maximum value you can get to. But that's really non-universal aspect. That would be a non-universal feature. That really would depend on your initial state, I think. Okay. All right. Okay, so let's do the same thing. I think I'm moving much slower than I anticipated, but doesn't matter. I think it's just, I hope it's okay if you think I'm going too slow or so, I can speed up. If we can just stay at this pace, then we're just going to cover a lot less, but we're going to cover it much more profoundly than maybe if we just go too fast. And please, students also, you know, jump in with questions if anything's unclear or you have something you want to ask. Okay, so now we do the same experiment in 2D. As I said, we do this with real random disorder. We have this very highly controlled disorder in the system. I just want to show you that really quasi-periodic and true random disorder are quite different beasts. You can even see it visually. I mean, I just plotted for you a 1D quasi-periodic potential here. This is 1D quasi-periodic. And you can see, and this is 2D real random with a Gaussian distribution of the on-site energies with a certain width, which gives us the scale of the amplitude of the disorder potential. And you can already visually see that these are very, very different things. So again, details might matter on what kind of distribution you have. So we have to watch out for that a bit. So here in this experiment, we're going to use true random disorder that we project onto the atoms. But the spirit of the experiment is the same. We start with a recognizable density pattern in 2 dimensions. We've evolved it for some time until we hope a steady state is reached. And then we analyze if any remnant pattern of the initial state is detectable in the experiment. Okay, if there is any memory of the initial state, whatever initial state we put in, this state, or that state, whether we can still retrieve it after some time, and hopefully, of course, we are in a steady state. Tomorrow, we're also actually going to discuss how you can measure that the system thermalizes. So that's something, a nice experiment from Marco's group in Harvard that I want to talk about tomorrow, actually. Okay, so how do we prepare that? Again, we're dealing, as I said, with the Bose-Hubbard model. We have the kinetic energy term, interaction energy, we have the on-site disorder, and we can, for example, create a stripe pattern or a domain wall by just removing half of the atoms to the right of the system. We do this in a quenched configuration when the atoms cannot move. Then we lower the lattice depth, and now they can suddenly evolve, and now we can see the dynamics in the system, and we look what's happening here. Again, this is a very high temperature state. This is actually even infinite temperature with respect to kinetic energy, because remember, any localized atom here, if you expand a localized wave function in terms of the Bloch waves, it's like an equal distribution of all the Bloch waves that you can have in the system. So that would be kind of an infinite temperature state with respect to kinetic energy in the system. So it's a high temperature state. So here's just qualitatively what we see. So this is the disorder-free case. This is the case with disorder, J being the tunneling in the system, tau denoting the tunneling times. That's just h bar over j. How long does it take to hop from one side to the next in a clean lattice? These are single snapshots to the left. So these pictures are single snapshots of the time evolution. And then if I average over many of those snapshots, you can see this thing here. And you can already see that for the non-disordered case, well, it happens what you expect to happen. These atoms from the left penetrate into the right region, and they are eventually confined by the harmonic trap. And eventually, after longer evolution times, you just see a homogeneous distribution of your gas in the system. In the disordered case, you see actually, well, it looks a bit different, because now you see that even after some longer evolution times, here 250 tau, clearly this has not evolved into a symmetric distribution. So this is not the thermal distribution. There's clearly still some remnant picture of this density wave in this system. And this we can again characterize by the imbalance. Again, how many atoms are to the right of the domain wall minus the ones to the left. Or if it's a stripe pattern, we have again this even odd imbalance we can calculate. And we can look at the time evolution for different disorder strengths, now up to 300 tau. And we see that actually for sufficient large disorder strength, this seems to approach a steady state in the system. And now I can plot the imbalance, this imbalance at this longest evolution time that I have available to me as a function of disorder strength. And that I see that the imbalance remains pretty much zero up to this, let me call it critical disorder strength, although we should be careful, I guess, with the wording here. If it's a crossover or whatever is happening here, at least I see there's a dramatic change. If I go to these larger disorder strengths here, then suddenly, even for very long evolution times, we have this steady state imbalance. If I look at the profile of the density pattern of the domain wall, it's just like a density-density correlation measurement, I actually see this is very nicely agreeing with exponentially decaying localization lengths that I can extract from these density profiles as a function of disorder strength. So I can plot this length scale, which is associated with this decay here, with this exponential decay, as a function of disorder strength. And this is this inset that you can see here. So I take just the psi from my density profile, I plot it as a function of the disorder strength, and you can see that actually this actually seems to diverge here at this, again, let me call it experimentally determined critical disorder strength, where the system seems to become localized in the system. There are another few cross-checks we can make. We can dilute the systems to make interactions less relevant. So this is the curve I showed you so far, was the light blue curve, where the imbalance picks up at some critical disorder strength. If we reduce the density of the particles in the system to make it less dense, less interacting, then we can indeed see that this critical point seems to shift to lower disorder strengths. And this is actually what we would expect, because for the non-interacting system, actually, if we would put non-interacting particles into our 2D disordered systems, we have a situation where we expect an arbitrary weak disorder pattern to localize the system. So for the 2D random potential, epsilon disorder strength for the non-interacting case localizes you. And once you're localized, remember the imbalance becomes non-zero. And this is what numerics tells us. So these are these points here. This is, we cannot measure but this. Unfortunately, in rubidium here, we don't have a Feshbach resonance, but we can actually calculate that nicely. So that's easy for the simulation to do. For the non-interacting case, we immediately expect for an arbitrary small disorder imbalance to be non-zero. Okay, so I think this all, at least conceptually, squares out with what we expect the system to behave. Let me just finally, at the end of the lecture today, let me show you just the different length scales that we can have, just to show you really longest time evolution. We can do this with a domain wall. This is what I showed you, but we can again also do this with this stripe pattern of this charge density wave that we can prepare and look at the time evolution. And this is what I show you here. So we started this stripe pattern here. We look at the evolution over now, the longest times that I promised you, 1,000 evolution times, 1,000 tunneling times. And we can indeed see here that for this order strength, in this case 24J, we can see that we approach this non-zero value, and it seems to indeed be in a steady state, the system here. So when I say seems to be, if we plot this on a log scale, actually let me show it to you here. If I plot it on a log scale, we can identify 3 different time regimes. There's a first fast decay happening on just few tunneling times. There's a slower decay happening on a few hundred tunneling times. And then there's this quasi-steady state. Let me call it quasi-steady state, because if you fit an exponential to this last part here, you would even find there is a decay at a even much larger time scale of 2,500 h⁻⁻J, at which we can say that's a kind of lower bound to what we can say how long this time scale is. It's probably higher within our error bars, but that's kind of a lower bound to the decay we can say where this comes from. And this again touches upon the points, what can we say and what can we not say in experiments. This would be, in our case, we would say this is most likely, this residual decay is because of couplings to the environment. Most likely because of couplings to the environment in our system. But of course, it could also be an intrinsic behavior of the system to decay still and be non-thermal and be thermalizing. And this is where it becomes very hard for experiments to say something any more than that, right? Where it really is then you have to try to see, if you have technical noise, does this thing become lower or larger, this decay rate, as you increase the noise or decrease the noise in your system? Okay, I think with that, I want to finish for today. I'm out of time anyway. Apologies, I ran a bit longer and we're going to cover less, but I think it was good to go slow and try to explain things in more detail. So yeah, I'm happy to, of course, answer any more questions that you might have. Let's go back to this point here.
I have a little we're going to zoom out question. When you went from 1D to 2D, you changed from fermions to bosons. Are any of the results related to that, or would you expect the same kind of behavior?
Yeah, I would expect, it doesn't matter. That's the nice thing with MBL. I don't expect, well, there's one subtle thing with bosons that you can, in principle, have arbitrary high occupation numbers that could potentially be an instability for bosons. That's again more an whereas for fermions, of course, you have Pauli exclusion principle. And if we're just confined to the lower band, we can just have maximum occupation of 2 on a site with spin up and down. That's a difference. So there's a potential big difference here. In practice, doesn't probably matter a lot because these higher occupation numbers are always cut off. And again, for the time scales we measure don't play a big role. So the short answer is no, I don't expect things to really depend. I think for fermions, it would have looked pretty much the same.
Okay, cool, thanks.
And of course, we're nice to do this for fermions with the Feshbach resonance again.
So what is 1,000 J in SI units?
This would be like a second or 2 in our system.
Okay.
And now you understand it's getting uncomfortable from an experimental point of view, when we have to say our couplings on that time scale, spontaneous emission, shaking, laser noise are not relevant. This is becoming uncomfortable. So this is, I would say, the largest time scale where we felt we were comfortable with quoting those numbers. It's genuine behavior of the system.
If you wanted to speed this up, would you be switching to lithium or something like that just tunnels more rapidly anyways?
Yeah, sure. That would be a good idea. Absolutely. So I think in our lithium quantum gas microscope experiment, this would be a nice thing. We didn't have as large system sizes at the time. We're working towards getting there, but this is absolutely a nice experiment to do. I mean, for that, absolutely. I agree. But you can run into other problems with lithium, but yeah, it's always a catch somewhere. Any more questions, comments?
So this tau2 of 105 h bar over j, how does
Yeah.
this depend on the quality of your bath and other things? Have you explored this?
The quality of what? Of the
Say the size of the bath or other system
but there's
parameters.
no bath. Well, here there's no. We're going to discuss in the next lecture. We're going to talk about baths. We introduce a bath into the system. Here there's no bath. Here there's no bath.
But I guess are there system parameters you can vary and see how this tau2 changes?
Well, the problem is we don't have very much handle on the interaction strength here. We expect this to depend on U, but since this is without rubidium, without a Feshbach resonance, we don't have so much handle here to do that. But yeah, that's of course the interesting question to predict from theory. Where does this timescale emerge from, this few hundred tau? That's certainly a non-trivial timescale. The very short one is pretty trivial, I would say. That's just hopping to the empty sites. That's just the fast dynamics of single tunneling dynamics. But the longer timescale, that's really genuinely interesting many body dynamics. That's harder to predict. And again, I mean, this thing you cannot run on a computer. We're talking about 200 bosons on about, again, 400 sites or something in 2 dimensions. There's no algorithm we know right now who can do this faithfully without, approximations.
And so you also don't have a lot of range to tune the disorder, is that right?
Oh, we do tune. No, we tune the disorder. That affects a lot. That will change. No, that's true. We tune the disorder. That does affect also this relaxation rate, and also tunes, of course, this offset that you see here. Yeah, absolutely. That's right.
Are there any further questions for this lecture for Immanuel? Because if you're feeling like you have questions building up, you have more opportunities than this one. Okay.
Just
all right. Yeah, and so in that case, the next lecture will begin in 25 minutes, I believe. Let me check to make sure I'm talking correctly. It'd be hilarious if I was wrong. Yes, indeed, in 25 minutes. And we'll switch from some wonderful experiment to some equally wonderful theory as we transition between these lectures. So I look forward to seeing you guys in about 20 minutes.
Okay, see you tomorrow. Have a nice day, everybody.
Thank you very much,
Lecture.
Immanuel.
Thanks.